3, 2, 1.
Hello and welcome. In this podcast, Innovating for the Earth, we're telling the story of an Australian company, Calyx, and how its groundbreaking innovative technology, which has been described by some as the reinvention of the kiln, has been used in many industries, cement, wastewater and more, to help them operate in a more sustainable way by, for example, reducing the amount of carbon dioxide they emit. In this episode, we're going to focus on what the Calyx technology is doing in the lime industry, and I'm joined by Vincent. Adam is a chemical engineer who's been with Calyx for over 11 years. He's previously been their General Manager of Research and Development and is currently the General Manager of Lime Decarbonisation, and it is indeed lime we're talking with him about today. G'day, Adam.
G'day, James. How are you?
Very good. Thank you very much for joining us. Let's talk lime. Let's go, before we get into Calyx and lime, what is lime? What is it used for?
Lime. Look, lime's it can be a bit of a catch-all term for a number of different products, but I mean, fundamentally, lime is calcium oxide, which is a chemical formula, a little bit boring perhaps, but it can also be used to describe calcium hydroxide, which is when you add water to calcium oxide, and sometimes it can be used to describe just limestone, which is calcium carbonate, which is the raw material that most people would know about because it's quite ubiquitous. It's used in a whole lot of applications, actually, James. So it's sort of early days. It was used as a mortar and things like that. So I guess our early ancestors probably accidentally made lime when they were stacking limestone around their fires and things like that. And by doing that, they converted the limestone to lime, and then it got wet, and maybe it mixed in with some ash from the fire and things like that. And they were able to make some crude cements and mortars and things. And so it played a big role, I guess, through the early centuries and things like that, just as a crude building product.
So to get from limestone to lime, the application of heat.
Application of heat, and that's fundamentally what we do as a business. We add heat to minerals, and that's how you make lime. Yeah, in this case, from limestone, calcium carbonate to calcium oxide, and CO2 is evolved in that process, which wasn't a problem for our early ancestors, but of course is a problem for us today with global warming and things. So just give us a sense of the size of the lime industry and the range of applications around the world. Yeah, look, it's a widely used product. Actually, in sort of 2020, around about 420 million tonnes of lime was produced worldwide, and that's a market size of about close to $50 billion US. So it's a significant market that most people probably don't appreciate in terms of the size. It's still expected to grow quite rapidly through to sort of the middle of this decade, to perhaps about 530 million tonnes. So it's still a growing business. I think that there's opportunities for lots of other applications in the future, and I guess we'll talk about that a little bit later when we get into the detail of the technology applications and things like that. But today, I mean, lime's used in some huge industries like steel and aluminium, pulp and paper, glass manufacture. Of course, it's used in agriculture, sewage treatment and water treatment. It plays a big role in scrubbing things like sulfur dioxide from exhaust streams and things like that. So it is a widely used product.
And in the building industry.
Yeah. I mean, fundamentally, cement that we know and love is fundamentally lime mixed with silica, with sand. That's sort of kind of the basic formula. So if you extend the use of lime into cement, that market size grows by about tenfold. So, but as a business in Calyx, we actually treat the two streams separately, even though it's the same reaction. You start with limestone and you make lime for use either as just a lime product or in cement, but we run two separate business streams in Calyx because we feel that they're a slightly different focus across the two different businesses. So I look after the lime side, and one of my colleagues, Dan Rennie, looks after the cement side, and we both come under the what we call the CO2 business, the LEILAC business within Calyx.
Yeah, and we've talked to Dan about Calyx's involvement in cement in another episode. So yeah, that was the cement episode. This is the other uses of lime episode. So just looking at those other uses of lime that you're responsible for, how much CO2 emissions do those other uses of lime contribute?
Look, individually, some of those industries produce a huge amount of CO2. Take steel, for example. Steel requires coal in a lot of cases to be made. Lime is added as an additive to help with the process. So the emissions from the lime in that case are quite small compared to the making steel, but they're still not an insignificant part of the footprint of steel manufacture. For example, aluminium fits into the same category. It's a big user of electricity, but it also uses quite a bit of lime, for example. But I mean, as a rule of thumb, when you make lime, you make a ton of lime, you produce about 1 ton of CO2. So collectively, if those industries are using millions of tons of lime, they're responsible, in effect, for millions of tons of CO2 emissions as well from that lime. So it kind of, in a way, if steel, for example, if steel can solve its its carbon issue around making the steel using hydrogen and these sorts of things, they still need to look at the lime that they use and neutralising the impact of that.
So now we're getting to it. We've got the lime industry, vital with so many applications, producing lots of carbon dioxide pumping up into the atmosphere. This is the crucial question. How can Calyx technology be used to reduce emissions in the lime industry?
Yeah, this is a lot easier with a whiteboard, James, and I'll try not to be I'll try not to be overly technical. But I mean, essentially, our technology, and it's been explained in other podcasts, but I'll quickly rehash. Our technology is a kiln. It heats up minerals, not unlike the technologies that have been around for centuries, as I said earlier. But the key and fundamental difference is that we keep the heating source separate from the mineral. So we feed limestone. It's crushed to a fine size, almost like a talc size. We feed that into a steel reactor, and on the outside of that reactor we apply heat. That means that the heat source and the mineral, the limestone in this case, are not contacting each other. So as the limestone moves through our reactor, it heats up, and as it heats up, it starts to produce carbon dioxide and lime. The carbon dioxide that's produced inside our reactor is a pure stream of carbon dioxide because it's not mixed with any it's not mixed with any gases from the fuels on the outside of the reactor. So by keeping it separate, we can produce a pure stream of CO2. This is the CO2 that comes off the limestone. Okay, this is an important distinction. We refer to that as the process CO2. The process CO2 accounts for around 70% of the total CO2 produced when lime is made. The rest of it would come from the fuel if it's a carbon-based fuel. So it's the process CO2 that we're capturing. On the fuel side, of course, there are the options to move to renewable electricity, for example, to provide the heat. Hydrogen. There's capture options for the fuel side that may work better when used in conjunction with our technology, because you're reducing the total load that those technologies have to capture from the stream. So it's the process CO2 that we're focused on, but we believe, with changes to the fuel sources and things like that we can achieve 100% CO2 capture, or effectively zero emissions lime.
So that's a great explanation of the process of how Calyx technology removes carbon dioxide from the creation of lime. Now let's talk about how you started working in the industry. How did Calyx begin to work in the lime industry?
Yes, when I joined Calyx around about 11 years ago, James, we were focusing on building just a small pilot plant, and our focus was on making magnesium oxide, which is similar to calcium oxide, of course. They both come from a carbonate form, so they both produce CO2 when they're reacted. The focus for the business at that point of time was around CO2 capture, but magnesium oxide was also seen as a potential product stream for us to allow us to get some early sort of establishment around cash flow and things like that. So there was a big focus on magnesium oxide, but we knew the prize was ultimately lime and cement. So the magnesium oxide was the introduction for us. The early reactors that we built, including the pilot reactor and our first commercial reactor, were built to make magnesium oxide. So fundamentally, they actually weren't designed with sufficient temperature, which is a key thing that I'll talk a bit more about when we get into the technology side a bit. But fundamentally, they weren't designed to make lime. But we were able to demonstrate small conversions of lime to lime from limestone. But I think fundamentally for us, building those reactors was really important for credibility, particularly the commercial demonstrator, because for making magnesium oxide, because we could point to that, and then we could go and seek funding to build a lime version of that plant. And by having one on the ground and of about the right scale, gave people confidence that we could do that. So in 2015, we applied for a Horizon 2020 European Union grant to build a demonstrator for lime and cement. And in 2000, we were successful in winning that grant, and that project kicked off in 2016 to build this demonstrator plant in Belgium. I was lucky enough to be the project manager for that project, and so I took my family across to Europe for a couple of years, and we worked on that project. And this was really the key breaking point for us in terms of not breaking in a negative way, James, in a positive way for us in this space. So through that project, we were able to demonstrate that fundamentally our technology could convert limestone to lime at a rate and an extent that was commercially viable. So that was a 5-year project. It had a big front-end R&D component to it, but ultimately we built the plant. We built the plant on time and on budget, and it, there were challenges, of course, but it fundamentally proved that we could work in this space.
Because it's all very well being, going to the market and saying this is a good environmental solution, we're going to capture the carbon dioxide, but you've got to prove that you're a good economic solution too, don't you?
Of course, yeah, that's right. And I think unfortunately, this space, because it's in its infancy, is a bit littered with technologies that sound good on paper but haven't quite proven themselves at scale. And I think through this project we certainly did that. We did enough, and we collected enough data to understand what our longer term operating costs will be, and our capital costs. And we feel we're very competitive in this space. I mean, ultimately the market will decide, of course, but the market's talking to us, so that's a good sign.
Yeah, you're in the game. You don't know if you're going to win, but you're definitely in the game.
Indeed.
And you're confident you're going to win, of course.
And we're confident.
Now, you mentioned challenges earlier. What were some of the challenges and problems, and how did you overcome and deal with them?
It's a good question. There of course were challenges for this project. That the fact that we were able to win government grant funding for this project meant there had to be challenges. Really, that the point of that program is to support mid-range technologies through to sort of commercialisation stage. So we had to show that there were a number of areas that we needed to scale up in, risks that we needed to address as part of the project. And I mentioned earlier about temperature, and temperature is really the key thing here. Magnesium oxide we can produce, let's say, at 750 degrees inside the reactor. To make lime, we need at least 900 degrees. And remember that our technology uses a steel reactor, and it's separated from the fuel source. That steel reactor has to reach temperatures in excess of 1,000 degrees, and preferably 1050 and maybe even higher, for us to achieve those temperatures inside. And this is it at the limit of even exotic steel capability. So, fundamentally, we had to show with this project that we could, continuously run a reactor at these sorts of temperatures, and they would not fail structurally. Of course, we didn't expect them to fail instantaneously, but over a period of time. I mean, this technology has to, these reactors have to last years before they're replaced. So we did that, but as I mentioned earlier, we had a front-end R&D component to this project, and that was critical. So we did a lot of testing with our partners. There was quite a few partners in this project. We obviously did a lot of testing. We did a lot of engineering, desktop engineering, looking at how the steels will behave at these temperatures. It's interesting because these steels, as I said, they're getting to the limit, and there's actually not a lot of data about how they perform at these temperatures. We were creating it effectively. So,
and were you surprised at any point?
I think we have been surprised at how well these steels perform at these higher temperatures. We were told in no uncertain terms by our engineering manager not to go above 1,050. But through the project, we pushed it higher than that. And that was. I hope I'm not giving away too many trade secrets. That might be edited out. But we pushed it beyond that, and and the steels have proven to be very good. So that was a key thing for us. Another couple of key risks for the project were, again, around the reactor, how the product might foul the inside of the reactor, because this is very important that we get good heat transfer from the outside of the reactor to the inside. And if you get material building up on the reactor walls, it can really reduce performance. I mean, this is a big thing in boilers and these sorts of things, right? But key for us as well. We had a confidence coming into the project because we'd had all the experience with our current plant running on magnesium oxide, but a slightly different product, potentially a bit more sticky and things like that. But all that's proved as we expected, which is fantastic. Corrosion is another issue. If the limestone has certain elements in it, like sulfur or chlorine, these can attack the reactor. So we needed to understand, at least initially, what those materials would do to our steel at these temperatures. So again, that was part of a big upfront program with one of our partners. They looked at fouling, they looked at corrosion. We built our confidence. We put coupons in the reactor and we pulled them out after a period of time, and they were inspected, and we looked at all those sorts of things. And the corrosion rates, which we knew there would be some corrosion rates, quite slow. We confirmed that they were slow and acceptable. So these were really important risk mitigation issues that we had to deal with within the project. Yeah, I mean, look, and of course there were other issues. This was an R&D project fundamentally. So, as we built it and started to run, of course you find other issues. And I think we always sort of comfort ourselves and say, okay, a lot of that was around the fringes, sort of outside of the core technology. So, issues with some flowability, but we understand why. We had issues with some of the fundamental aspects of the project, burner supply and all these sorts of things. But that's just a project of this scale. You're going to get those sorts of challenges. And of course, the biggest challenge was meeting budget, James. And so our budget for this project.
Did you?
Hey, yes, we did. And but you've got to. I mean, you need to have you need to have plan Bs all the time, right, with these things, because you want to build everything, but the reality is you can't. And so there was always, through the project, there was always a case of we'd love to have that, but we can get away with this. And as as things got tight, we had to say, well, we have to ditch that, but we can't lose this fundamental piece. And we managed to do that, and we managed to bring the project in on budget. So yeah, lots of challenges.
Yeah, wow. And so now you've been through that process, which is essentially a process of experimentation, of learning, of refining, of improving. What does the future hold for Calyx in the lime industry? What are the plans, as much as you're able to share?
Yeah, look, so I mentioned earlier about the slightly separate focus between lime and cement, and I think it gets important now for this discussion because let's say we've got a bit where we think commercially we're a little ahead on the lime side. The cement piece is currently involved in a scale up of the LEILAC 1 project, which was the project I was talking about. LEILAC 2, it's looking at multiple tubes and all sorts of things. The lime industry is smaller. The calciners are smaller. So even a single calciner of the size we built in the LEILAC project could be a commercial size plant. So our focus in lime is more now around commercialisation. But we do accept that we're still coming from effectively an R&D project to a commercial plant. So the language we use is commercial demonstrator. The expectation is that we'll be building calciners that are commercial, but may need a little bit of technical development. And that's the conversation we're having with the industry, and we're getting a good hearing. Not every manufacturer wants that. Some of them don't want any risk. But they do realise that they've got this CO2 challenge in front of them, and they're talking to us. So we've got a few projects now into feed studies, which is great. So I'm hoping that over the next couple of years we're bringing on multiple commercial demonstrators in the lime space.
And more broadly, what do you see any big changes that might occur in the lime industry over the next decade? Yeah, look,
it's initially the lime industry has the CO2 issue they have to face. It's hitting some of them already. So clearly there'll be change in the industry over the next decade, or 30 years really, if we take all of the time to get to net zero. But I think the reality of carbon pricing, particularly in Europe, and I think that's starting to spread out around the world now, is that these companies will have to act sooner. So I think there'll be initial take up. I don't think companies will necessarily 100% go to CO2 capture for their fleet, because they don't have to. And of course, there's a huge cost associated with that. So I expect that we'll start to, from Calyx's point of view, we'd like to see, if there's 3 calciners on a site, we'd like to see one of them as a Calyx calciner first off. And then, of course, we grow out from there. And I think that's the industry. I think the industry they'll be taking bites to get their CO2 footprints down. They might be changing fuels, looking at our type of technology and these other capture technologies and just sort of start to scale them out. But it's a huge challenge. We're talking half a billion tons of CO2 capture potentially in this industry. So that's not going to happen overnight. It's a huge task. And I think the reality is there'll be a sharing of technology across that challenge. And obviously we're hoping we're a big part of that. The lime industry in this space, the lime industry has some bigger opportunities actually. Lime currently isn't really used for the absorption of CO2, but it can do that. So if you make lime, if you expose it to a rich CO2 environment, of course the CO2 can go back onto the lime and you can make limestone again. So you can absorb CO2 from different processes this way as much as you can drive it off the lime. So if you capture the CO2 when you produce the lime in a Calyx calciner, for example, and then you go and absorb CO2 from another application and bring that limestone back, in fact you loop it, through this process, and you're storing the CO2 as you're calcining it, then you can use lime as an absorber of CO2 from different processes. So there's a play here.
Right. And then what do you do with all that limestone?
Well, the limestone just loops around effectively, James. So the lime collects the CO2. The limestone comes back to the Calyx plant. We calcine it again. We store the CO2 that comes off, and then the lime goes back, gets turned into limestone, and effectively you've got a looping system where you're taking CO2 out of another process, and you're effectively then storing that after you've calcined it again. So it's referred to as calcium looping, and it can be applied to lots of different applications. We've recently been talking to the shipping industry. Shipping's a huge contributor to global warming, as is cement and these sorts of things. And they're looking for options. Now, one of those potentially, and we've been talking to them, is can we put lime on a ship? Can we absorb the CO2 from their exhaust stream on the ship and make limestone, return that limestone to the calciner and calcine it again, and we have a loop set up. The interesting thing about this particular application...
Oh, wow.
Yes. The interesting thing about this particular application is that when you absorb the CO2 from the exhaust on the boat, you actually produce energy. Okay, so when you take the CO2 off the limestone, it uses energy, but when you put it back on, it produces energy. And if you can recover some of that energy or most of it and put that and help drive the boat with that, then you can cut their fuel emissions as well, their fuel consumption. So the whole concept...
Fantastic.
Well, it's a really interesting idea. It's got a little way to go, James. I'd put it quite low on the TR scale, but the concepts are real. I mean, it's just another form of what we call calcium looping. And there are other examples of this. You'll hear about, and things like direct air capture is becoming a catchphrase, and that's where CO2 is actually directly absorbed out of the atmosphere. And this is being talked about because there's a belief that we'll have to be taking CO2 out of the atmosphere, not just stopping putting it into the atmosphere. So one of the ways of doing that is to actually remove it directly from the air, and you could potentially use lime in that kind of situation.
Yeah. Yeah, that's very interesting. Adam, before you were General Manager of Lime Decarbonation at Calyx, you were General Manager of Research and Development. Moving beyond the lime industry for a moment, what do you see as the main challenges and opportunities for Calyx over the next few years?
Yeah, look, I think the challenge for us as a business is that we have to maintain innovation. We're built on innovation, James. You have to maintain innovation, but you've also got to get commercial, right? So it's that balancing act now of maintaining innovation while we grow the business, to stand on its own 2 feet. And that's a challenge for sure, because it requires that ongoing commitment to innovation. And we've been very innovative. The business is built on innovation, writing patents, these sorts of things. But we've also been heavily supported by government with grants and tax rebates and all these sorts of things, right? But now it's time for the business to become commercial. So that's a challenge. But I think the opportunities on the other side are, I think, yeah.
Almost paradoxically, when businesses start with a groundbreaking technology like Calyx's, they have to be innovative to survive. And paradoxically, when they get some success, it's often the most challenging time for innovation because everyone kind of thinks, oh, we can relax now, we're doing it right, let's just keep going. So it's great that you've identified that as a challenge. Success can actually remove the terrifying need to be innovative and make everyone feel a bit comfortable.
Indeed. bites the nails of innovation or something like that, So I think that is it. Yeah, I think that's definitely a challenge for the business. I mean, we absolutely got the right people running the business and things like that at the moment. And I think it's the innovative side of the business that still attracts investors and things. So it is just a matter of keeping the balance as we move forward. But yeah. I think on the opportunity side, it's almost endless. We've touched a number of the carbonates, magnesium carbonate, calcium carbonate, but there are many processes that use kilns and calciners in their processes. And I think what we're really learning is that apart from CO2 capture, apart from carbon dioxide capture. Our calciner does two other things really well. One is it's temperature control, so we can raise the temperature of the product to exactly the temperature that it needs to be, and not overcook it, which is a big problem for a lot of kilns. That they tend to have to overheat the product to get a result. And the other one is that we can control the atmosphere inside our reactor, and this can be very important if you don't want oxygen or these sorts of things. I mean, it's a little technical, but because it's separated from the rest of the process, we can make the atmosphere whatever we want, essentially. So we could add hydrogen, for example, and keep air out. So we can do those sorts of reactions and things like that. So, I mean, a good example is we have a project at the moment where we're looking at calcining a lithium-containing ore called spodumene, and if you can calcine this material and not overheat it, you can avoid melting some of the silica and making it sort of glassy, and that's really beneficial for extracting the lithium from these grades. So the idea that we can just hit that temperature but not go any higher is really beneficial in that kind of application. So we've got a project underway at the moment in feasibility study, and we're hoping that turns into something. There's quite a few other areas that we're looking at, but actually that's another division within Calyx that we call sustainable processing. So you may or may not talk to the general manager of that project at some point in the future, but of that area. But
indeed,
yes. So lots and lots of opportunities.
A lot going on.
Indeed.
Finally, a more personal question. In your time at Calyx, one highlight and one lowlight.
One highlight.
Just one.
That's tough. Yeah, and lots of things. Look, I think winning the LEILAC grant was so important for us. You know, it was the culmination of years of work, recognition that the technology could work for that application, really credibility. You know, it gave us a lot of credibility and recognition. So that was incredible. And I also got the opportunity to live in overseas for a couple of years. So it was and manage that project. So that was a real highlight. Lowlights, there hasn't really been many actually, but we as a business, we were a startup, so we went through the valley of death, as most companies go through, where you're still trying to convince investors that you've got something worthwhile. And of course, most of these companies aren't overcapitalized, so things get very tight. So there was a period there where we were waiting for that next big investment to come. It came eventually, but in the interim, there was bootstraps, as our CEO likes to call it. And get through, but we did that. But yeah, that was a stressful period for sure. Yeah,
I'm sure. Well, good on you for getting through it. The future looks really interesting. Adam, thank you so much for joining us on Innovating for the Earth. Well done.
Thanks, James.